then when I finish these notes, I want to get partway through the 5.3. All right, so today this is a lot of definitions, okay, a lot of definitions. So 5.2 is on what's called the extreme value theorem. So we've done the intermediate value theorem and we've done the mean value theorem. So this is our third one that are called existence theorems. So before we hit that, let's get some definitions in. We have what are called global or absolute maximum. And maximum and minimums are referred to as extrema, okay? So for the global or absolute maximum, f of c is the absolute maximum value of f of x if and only if f of c is greater than or equal to f of x for all numbers x in the domain of f of x. In other words, it's the highest y value anywhere on the graph, okay? It's kind of simple. I will typically be using absolute maximum. They're synonyms, global and absolute. I mean, global, I think you know, big picture overall. But it's sort of the difference between older language versus more current, contemporary is absolute. Then a local or relative maximum is kind of in a region or in a neighborhood, and I will be using relative maximum. Global or absolute minimum is really the lowest y value anywhere on a graph, and a relative minimum is kind of in a neighborhood. I think it's a valley, and my relative max is a hill. So if you look at this diagram here, A is called an absolute minimum. It is the lowest y value on this interval. B is what we call a relative maximum. So as you come in from the left and the right, and maybe we kind of do this, this might help. You see, this is where B is. If in this neighborhood, B is higher than the values to the left or to the right, then that's a relative maximum. C is referred to as a relative minimum. And again, in that neighborhood, it's the lowest point. Then D is the absolute maximum. Now D is also a relative maximum, okay? So it is possible to have both names. But typically, if it's the absolute, then we don't call it the relative, but technically it is a relative. All right, so what I want you to notice, and I'm planting some seeds for really 5.3, do you notice that at my relative max, if I look at my slopes of my tangent lines, what do you notice? They're zero, okay? That's not an accident. That is on purpose. For some books, and if we look at this next one, A and E are locations of a local maximum. Other books call them endpoint maximums. The good news is on the AP exam, they're not going to give you, like a question like that because it's ambiguous depending on what textbook you use. But B is the location of an absolute minimum. C is the location of the absolute maximum, and D is the location of a local minimum. Do you notice that B and D, the derivative does not exist? So, relative max and mins can be where the derivative is zero or does not exist. So again, I'm planting seeds. Not all functions have a minimum or a maximum. So if you look at the graph on the left, do you see there's a vertical asymptote there? And then it's shooting up to infinity or down to negative infinity. So there's no minimum or maximum, no relative, no absolute. The graph on the left, do you see that those are actually open circles on the endpoints? So it never, so think about our limits, the idea of a limit. I'm getting closer and closer to letter B, but I never actually reach it because of the open circle. So there's no max or min there.
And it's not just infinitely close to B, it's a limit.
Okay, so a maximum has to be a defined value. Yeah, it does have to be a defined value. Great question. Again, a function does not have to have a maximum or a minimum on an interval. Now look below. This is on the interval, closed interval -1 to 2 for figure 1. So do you see there's dots? I do have a minimum, and I do have a maximum. Do you see that on figure 1? Here's a minimum, a global or absolute minimum, also a relative, and then I have an absolute maximum. But look at figure 2. I do have a minimum, but why don't I have a maximum there? Dylan? Yeah, because that endpoint here on the right is open, okay? And then look at the one in figure 3. This one has no minimum, but it has a maximum. So do you see the minimum? There's an open circle there. All right, so I did want to show you a variety of possibilities here. So then, in the blue box to the right, here's the extreme value theorem. If f is continuous on a closed interval, a to b, then f has both a maximum and a minimum on the interval. So I want you to look at figure 1. That was the only one that met those criteria. It's continuous and it's a closed interval. Do you see in this one? It's an open interval, and on this one, it's not continuous. You see that connection to the extreme value theorem. So the graph of f of x equals x cubed minus 3x squared to the right has a relative minimum at 2, -4, and it has a relative maximum at 0, 0. To make this easier for you, think of the relative maximum as being a peak of a mountain on the graph and the relative minimum occurring as the valley of the graph. Note that if these peaks and valleys have smooth, rounded curves about them, then the graph has a horizontal tangent line at those points. Note that at each relative extrema, the derivative is either 0 or does not exist. The x values at these special points are called critical numbers or critical points. So I'm going to use that interchangeably, critical numbers or critical points. So a critical point is a point on a function graph at which the derivative is either 0 or undefined. They are important, even critical, because relative extrema and even absolute extrema can but don't have to occur at such points. In other words, a critical point is a point that has a possibility. So let's use our highlighter. A critical point is a point that has the possibility of being an extrema. It doesn't guarantee it, but it gives us that it's a possibility. Below are 2 examples of a critical number c of function f. So the one on the left, that's where f prime of c does not exist. And on the right, that's where f prime of c equals 0. If f has a relative minimum or a relative maximum at x equals c, then c is a critical number. Now, the converse is not true necessarily. So how do you find a critical point? You find the derivative and try to set it equal to 0. The x values where the derivative is 0 is a critical point, or where the derivative does not exist is a critical point. So I'm going to pause a moment, and I want you to find the derivative first in these 2 examples. On letter A, I think you can easily find where the derivative is 0. All right, so letter A, did you get f prime of x was x squared minus 9? That factors, you set it equal to 0. Make sure you are showing setting equal to 0. So x equals plus or minus 3 are critical points. All right, for letter B, I'm going to first rewrite this as 4 minus x squared to the negative 1/2 power. Then g prime of x, you bring down the power, decrease the power by 1, and then we're going to do the chain rule. Now, you do need to make a note here. In g of x, the domain, x cannot be plus or minus 2, because that would cause me to divide by 0. And then also, if I would solve that, doesn't x have to be between negative 2 and 2? Like I can't put 3 in there, or 2.5. So you do need to stop and think about the domain of the original function. So, and really, it'll be negative 2 to 2 is my formal domain. So just keep that in the back of your mind here. So let's tidy this up. The negatives cancel, the 2's cancel, and I get x over the square root of 4 minus x squared cubed. So critical numbers are where the derivative does not exist or where the derivative is 0, provided that's in the domain of your function. Okay? So where is this derivative equal to 0? Well, that'll be at x is 0. Okay, that's where g prime of x is 0. And it's undefined at plus or minus 2. Now you stop and think about your domain. X equals plus or minus 2 is not part of the domain of g, so it cannot be a critical number. So we're going to cross that out and say x equals 0 is the critical point. So be careful. Be careful with this. All right, questions on finding critical points or critical numbers. They're the same thing. So find the derivative, set it equal to 0, find where the derivative is 0 or undefined. Be careful to check the domain of the original function. All right, in 1 and 2 below, it says find all extreme values. Extrema, okay, extrema or extreme values are your maximums and your minimums. So what I want you to do, I'm going to give you a moment, and I want you to find absolute or relative, max and min. And on the one on the left has a tricky part to it, but if you really look at the technical definition, and that's what we're going to really tease out here, is a relative max or relative min is a location on the graph that is higher than the points to the left and to the right of it. So be careful in number 1 and even number 2. All right, in number 1, do you see that there is, and I want to make sure I'm really clear, we don't call max and min's points, okay? We don't call them points. We say it's the y value, and then we do describe the location of that y value. So the absolute max, whoops, Hopefully it's coming back here. There we go. Okay, so there's an absolute max of okay. What's the absolute max on this graph? 5, and it occurs at x is 0. So that's how we write these. There is an absolute minimum of 1, and that occurs at x is -3. Now, what do you think about any relative extrema? Is there a location where there is a value that's either higher than the others in that region or lower than the others, but it's not the absolute max or min? Yeah, Katniss? Awesome. All right, good catch. So there is a relative minimum. So look, when I look in this neighborhood, this point is lower than the points to the right, and it's actually lower than the points on the left. So good catch. Yeah. Oh, absolute is different from relative. Okay, relative is the one in the neighborhood that you need left and right. Absolute is the highest over the entire closed interval, and the absolute minimum is the lowest anywhere. So you're not looking in the neighborhood. Okay. Great question, great question. So then let's look at number 2. Is there an absolute minimum? Is there a point lower than all the other points on the graph? No. Is there an absolute maximum? Yes. There's an absolute maximum of 3, and it occurs at x equals -1. All right. Okay, this is tricky. Then do you have a relative min or relative max now? There's a relative max of 1, and it occurs at x is 1, because if you look in that neighborhood, that point to the right and to the left, it is the highest in that neighborhood. All right. Yeah, Ryan?
So, if the value like -3, if that was a close circle, would it be a relative, would 1 still be relative max?
So if the dot at x is -3 were closed, that it can't be relative because there's nothing on the other side. Relative extrema you have to be able to look left and right in the neighborhood. Absolute is the highest or the lowest anywhere on the graph, and it doesn't matter the neighborhood. So if I close this one, it can't be a relative because it's the end of my interval. All right, so the 3 value theorems. Note what the intermediate value theorem, IVT, the mean value theorem, MVT, and the extreme value theorem, EVT, have in common. All 3 guarantee the existence of a function input that has a certain property. Any AP problem that asks you about the existence of a function input with a certain property is almost certainly asking you to apply one of these theorems. So let's consider just some quick questions. It says, consider each of these functions on the closed interval 0 to 6. So in example 1, is this continuous on that interval? Yes or no? No. Does the function have an absolute maximum? No. Does it have an absolute minimum? No. In example 2, is this function continuous on the closed interval? No, because of those open endpoints. Does the function have an absolute maximum? No. Does it have an absolute minimum? No. Example 3, this one's going to get a little tricky. Is the function continuous from 0 to 6? No. Does it have an absolute maximum? But is it a value, a number? No. How about the third question? And this is the one that I think is tricky. This is a closed interval from 0 to 6. Does it have an absolute minimum? It actually does, because this is stopping at the point 6. So it does. It does. So be careful with that type. All right, example 4. I'm going to pause a moment, and I want you to answer the 3 questions. Think about it before I fire off the answers. All right, is the function continuous? No, there's that open circle. Does it have an absolute maximum? Yes. Where is it? You got it. Okay, do you see that? On that closed interval, 0, 4 is in fact the absolute maximum. Does it have an absolute minimum? No. All right, so you try. Graph a function defined on the closed interval 0 to 6 that has the properties indicated. An absolute maximum at x is 6, absolute minimum at x is 0, and continuous everywhere but x equals 6. Think about it. See if you can come up with a drawing. Okay. All right, so Skylar's going to put one up for us. So as I'm walking around, a lot of you have the same thing. So you have, it's continuous everywhere but at x is 6. So I think, don't you need, yeah, you did it. I thought you had it on your paper. Yeah. So that one's closed and the other one's open. Yeah. All right, so the absolute max is at x is 6. So that point had to be above the other ones. It has an absolute minimum at x is 0. But it's not continuous at the 6. Now, do you notice, and I'm going to put the one I had, which is really, really quite similar. It just says the minimum is at x is 0. It doesn't say the y value is 0, right? So, like, it's fine. His drawing is absolutely fine. All right, let's try another one. Graph a function defined on the closed interval 0 to 6 that has the properties indicated. The absolute max is at 2. The absolute minimum is at 4. And continuous everywhere but x equals 0. careful. It says it's defined on the closed interval from 0 to 6. So I have a lot of you that have an open circle, but it's defined. So what do you need at that spot?